Hello students. Continuing our lectures on nanoelectronics, we will first start with the concept that in nanoelectronics or any nanotechnology, basically what we are doing, we are uh, involved in the process of miniaturization. And this process of miniaturization has shown properties of materials and also devices which are different and beneficial. The reason for that beneficial properties is mainly because of the quantum size effect occurring. Now, all devices, especially when we talk about nanoelectronics, all devices in electronics or nanoelectronics have a common small island, have something in common, and that is there is a small island composed of semiconductor or metal. In which electrons are confined. Electrons are confined. Now, this island of a nanoelectronic device, this island of a nanoelectronic device, assumes a rule analogous to that of a channel in a field effect transistors. Same rule. As a channel in FET. Now, what is a channel? In a field effect transistor, there is a source, there is a drain, and there is a gate. So, any voltage applied to this gate, it governs, it regulates the current that flows between the source and the drain, and the area through which the current flows is actually called the channel. And so this island plays the same role as the channel as in an FET. Now, another thing is the confinement. So the extent of confinement of the electrons is also a very important parameter. The dimensions in which they are confined. And there are basically three basic categories of solid-state electronic device based upon the extent of confinement. Basic categories of solid-state nanoelectronic device. So these are first there is a quantum dot, which has got 0 degree of freedom. Then you have something called a resonant tunneling device. RTD, which has got either 1 or 2 degree of freedom. And lastly, we have something called single electron transistors, which has got 3 degrees of freedom. So these are the 3 categories of nano electronic devices based upon the extent of confinement that is taking place. Now, there are other control factors which permits the designer of the device to employ quantum effects in different ways, and to control the passage of electrons to and off the island. So it actually controls the passage of electrons onto and off the island. Onto and off the island. Onto and off the island. Another important parameter is the mean free path of the mobile electrons. Which can be much greater in semiconductors than in metals. Therefore, greater in semiconductors than metals. Therefore, what happens is that the electrons might travel coherently all the way across the semiconductor, and then without severe collisions, travel coherently all the way across the semiconductor. Electron island without any severe collisions. And due to this, what happens is that this leads to the conductivity of the device can be strongly enhanced. Enhancement of conductivity of the device. Or suppressed by quantum mechanical interference between separate paths an electron might take through the device. Or suppressed by quantum mechanical interference between separate paths. An electron might take through the device. And mobilities of electron are higher in these has been found in higher in 3-port semiconductors. So if you compare the normal semiconductor silicon and germanium with the 3-port semiconductors, it has been found that the mobilities of electrons are higher in 3-5 semiconductors, and it is also easier to fabricate defect-free junction between different 3-4 conductors. So also there is a, I should say, easy defect-free fabrication of these 3-5 semiconductors. Now, the smallest dimension of the island in a solid-state electron device is 5 to 100 nanometers. This is the smallest dimension of an island. Smallest dimension of an island, and the island may consist of a small region or layer different from the surrounding material. So island may also contain a small region or layer different from the surrounding material. Otherwise, the edges of the island may be defined by electric fields. Now, the reason is that it is not this way. Otherwise, the edges of the island may be defined by electric fields from small electrodes patterned may have electric fields from small electrodes pattern in the shape of designed island boundary, patterned as island boundary. Now, what happens is that often we can find the island is embedded between two narrow walls of the same other material. Often the island is embedded between two narrow walls of the some other material. Two narrow walls of some other material. Or it can be an insulating oxide of the island material, or an insulating oxide of the island material, or insulating defect zone in the substrate, or an insulating defect zone in the substrate. So, in any case, therefore, the island is surrounded by potential energy barriers. So, in all the three cases, it's common that island is surrounded by potential energy barriers. Which actually impede the movement of electrons in and out the island. Now, consider the energy versus distance diagram. Plot energy versus distance diagram. It will look something like this. Now, this is distance and this is the energy. These are the unoccupied levels, and we do have a Fermi level here. Same is the case with this. Some unoccupied levels, a Fermi level. Some unoccupied levels. Then we can have the Fermi level, and again unoccupied levels. So this corresponds to the conduction band, and This is the first excited energy state of n+1 electrons. First excited energy state of n+1 electrons. This is your delta E, and this is also delta E. This one is U, and this one corresponds to the Allen region. This corresponds to the Allen region, whereas these regions correspond to the barrier region. And there is a metal contact discussing on both sides. This one is the metal contact, and this region, the barrier region, is made up of white bandgap semiconductors like aluminum arsenide, and the Allen region is made up of narrow bandgap semiconductors like gallium arsenide, and that of course the middle contact. So this is the basic structure or quantum well for resonant tunneling diode. The barriers, as you can see, create the potential energy well. Now, the energies of the electrons trapped in the well are quantized. The energies of electrons trapped in the well, those energies are quantized. Now, the mobile electrons in the source region. So one of the regions is the source, another region is the drain. So one of the potentials, so we have shaped like this. So this corresponds to the source, this corresponds to the drain, and mobile electrons in the source region and drain region occupy energy levels between band edge and the Fermi level. So you see that the mobile electrons in S and D, that means source and drains, and they occupy energy levels between band edge that means the extreme of the band and the Fermi level. Now if n mobile electrons are on the island, let's say there are n mobile electrons on the island, the energy cost of adding one more electron from the source has two components. So if we would like to add one more electron, add one, so that to make it n+1, so the energy required has two components. Energy required to add one electron has two components. the changing energy U and the excitation energy delta E. The changing energy U and the excitation energy delta E. So let's draw it once more. So it was like this. So this is your U. This amount of energy is the U, where you are adding one electron, and there is this. This is the excitation energy delta E. So as we keep on giving excitation energies, it will rise one electron one by one. Now, within the island, the mobile electron will tend to form a puddle. So within the island, the mobile electron will tend to form a puddle. One second. Now, literally a puddle means a very small pool of usually dirty or muddy water. So it forms a small pool of electrons, and so you have an island. Between that island, you have some small pools of electrons made up by the mobile electrons, and this puddle is surrounded by a depletion region. So this puddle, or the small pool of mobile electron, is surrounded by depletion regions, because electrons in the puddle are repelled from the surface changes that collect on the boundaries of the atom. This is because the electrons in the puddle are repelled from the surface changes, from the surface charges, from surface charges and the boundaries of the element. Boundaries. Now, the physical features that form the island may have to be fabricated many times the size of the usual region of electron, and this one factor that works against the miniaturization of such quantum effect and single electron solid state devices is the physical features that form the island, and it has to be fabricated many times. Now, despite the fact that the depletion region confines all electrons to only portion of the island, now the depletion regions are restricting the electrons, are confining the electrons in the puddle, as we have told. In spite of that, the physical features, or the physical factors, let's say physical features like the shape and size of the island. That is very important, and that needs to be taken into consideration. Now, the two essential quantum mechanical effects are to be exhibited by electrons confined there. Firstly, so the electrons need to show two quantum mechanical effect when they are confined inside the puddle, which is inside the island. The first one is that restriction of each electron's energy. So first of all is the discrete quantized energies. This is the first effect. And the smaller the distance between the barriers, that is the smaller the island, the more widely spaced is energy levels. So smaller the distance between the islands, the wider are the energy levels. Wider are the energy levels. And as we have told you, delta E is actually the energy difference between two levels. Now, if the potential barriers are thin enough, barriers are thin. By thin we mean 5 to 10 nanometers. This is the thickness of the barrier, or less. Electrons occupying the energy levels lower than the height of the barrier have a finite probability of tunneling. So the tunneling process may occur. Electrons may tunnel through the barrier to get onto another island. However, there has to be an empty state within the same energy level waiting for the other side. However, the condition is that there has to be an empty state of the same energy level. Now, so first of all is the size effect. That means the closer is the island, the wider is the energy gap. And second is that if the barriers are thin enough, there can be a tunnel of electrons from one island to another, even if the energy potential is more than the electron energy. Now, these two effects of energy quantization and tunneling, they strongly influence the flow of electrons through the non-electronic device. Now, the question is when a bias voltage is applied. When a bias voltage is applied across the island, it induces mobile electrons in the conduction band of the source region to attempt to move through the potential well in the island region to get to the region of lower potential in the drain. So source, which is at higher potential, when we are applying a voltage, the electrons may move from the source to the drain, which is at a lower potential, lower energy. And this, as we have told you, this movement from source to drain is through the island region. So we have an island present in between the source and the drain. Now, the only way for the electrons to do this is to tunnel on and off the island region through the two high potential barriers. So there are two barriers. In spite of that, electrons, the only way they can do it from the source to drain is when they keep on tunneling through the islands in between the source and the drain. So on and off the island they can tunnel, and that is how the electron flow takes place in the non-electron device. So there is tunneling, there is island formation and discretization of energies to island. Closer island, the higher is the difference between the two energy levels. So this is how the electron flow takes place.